Land exposed by melting glaciers transforms into a greenhouse gas emitter. Sediment hidden under ice for millennia is seeing daylight again as glaciers melt. At first, those fresh minerals mop up carbon dioxide. But over time, they switch roles and start leaking gases that trap heat in the air. Researchers compared young glacial meltwater with soil water that had been exposed for about 10,000 years. Their work shows why every newly uncovered valley enters a long, slow countdown from sink to source. After glaciers melt, methane rises. Lead author Andrea Payne and co-author Jonathan Martin sampled streams that draw melt straight from small glaciers and others fed by seeps through mature tundra soils. The two waters could be told apart by their oxygen isotopes and by how clear they were. Meltwater ran chalky with rock flour, while seep water ran tea-colored from dissolved organics. Our central hypothesis was that the transfer of greenhouse gases between landscapes and the atmosphere has changed since the last glacial maximum about 15,000 years ago, said Martin. Field data upheld that hunch, showing glacial streams still scrubbing carbon dioxide while older soils were busy making methane. Freshly ground carbonates and silicates react with carbonic acid in cold meltwater, locking up carbon as bicarbonate. Once microbes colonize the maturing soil, they chew on buried plant matter and turn it into methane through methanogenesis, reversing the sign of the gas ledger. Glacier melt reshapes gas timing. Methane packs a bigger punch than carbon dioxide, trapping about 28 times more heat over a century. Nitrous oxide, the third place greenhouse gas, is even fiercer, with a global warming potential of 273 on the same scale. Those numbers mean that a late rise in methane can wipe out the early carbon dioxide savings that bare sediment briefly earns. Climate models trying to look centuries ahead need that timing baked in, or they risk undercounting the payback later in the game. Martin's crew found that the window of net uptake might last only a few centuries in the high Arctic. That's just a blink compared to the 10,000-year age of most post-ice soils. That insight adds a moving target to projections of future warming. Greenland's valley tells all. Kavafjord lies about 6 miles southwest of Nuuk and covers roughly 12 square miles. Only 1.7% of the watershed still holds glacier ice, yet the lingering meltwater strongly flavors the downstream chemistry. During a clear July stretch, meltwater from nearby glaciers ruled the flow, and carbon dioxide in the main channel stayed close to atmospheric equilibrium. A week later, cloudier weather cut the glacier melt pulse, seep water took over, and methane levels at the outlet jumped more than fourfold. That flip also showed up in the strontium isotope gap between water and bedload sediment, a geochemical clock for weathering progress. Values near zero in seep streams told of minerals already well chewed, while high values in the icy headwaters marked rock that had barely started to dissolve. Field calculations revealed a net sink of 64 millimoles of carbon dioxide equivalents per second during the melt-dominated period. Just days later, the same outlet turned into a 44 millimole per second source as methane outran the shrinking weathering sink. Reading the gases. Carbonic acid weathering of carbonates and silicates pulls carbon from the air, but sulfuric acid weathering of carbonates can add it back. The balance between those paths hinges on how much fresh mineral surface and dissolved organic carbon each water source carries. Runoff from glaciers had lower organic carbon, yet it was more labile, fueling acid generation that sped up mineral reactions. Seep water, richer in tougher humic carbon, fostered anaerobic pockets where methane-making microbes thrived. The study underscores that melting ice and deglaciation is not a single event but a sequence of chemical stages. Understanding which stage a watershed occupies helps predict whether it will cool or warm the planet in any given decade. Warming builds after glacier melt. Payne and Martin now plan to test nitrous oxide dynamics in the same valley, because that gas can warm the air 200 times faster than carbon dioxide if it escapes. Preliminary lab work hints that nitrous oxide might peak earlier than methane, suggesting a still more complex handoff among the three gases. Other researchers are already noticing similar trends elsewhere. On the Tibetan Plateau, lakes that no longer receive melt from glaciers emit about 3 times more methane than glacier-fed lakes. As more high-altitude or high-latitude basins lose ice input, those findings imply a widespread tilt toward methane dominance. Martin cautions that rapid, human-driven warming could briefly revive the negative feedback by boosting meltwater flow. Yet the reprieve would be short-lived. Once the last ice patches vanish, soils everywhere will settle into the methane-rich phase that the Kabefdor team measured. The study is published in Communications Earth and Environment. Like what you read. Subscribe to our newsletter for engaging articles, exclusive content, and the latest updates. Check us out on EarthSnap, a free app brought to you by Eric Rawls and Earth.com.